Hi folks, today we're going to talk about the volume of pyramids and cones. And I'm sorry that my, this is kind of blurry a little bit. There's not a whole lot that I can do to make this better because the lighting in the room that I'm in is kind of funky. But the volume of a pyramid, let's start out with that. So the volume of a pyramid with a base area of capital B and a height of h. So remember that height is the distance from the vertex to the base perpendicularly. So vertex to where the base would be perpendicularly, so at a right angle. So the volume formula is V equals 1/3 times the area of the base times the height of the pyramid. So in example 1, it asks us to find the volume of the pyramid, so we're going to use that formula. There's a lot that goes into some of these problems, especially if your pyramid is not like a square or rectangular pyramid. If it's a hexagonal pyramid, for example, it gets a little bit more difficult because in the formula, the area of the base is the area of this hexagon. And so the area of a hexagon, and I want you to assume that these bases for the polygons are regular. If it's not given to you that it's regular, then I want you to assume that it is regular in these problems today. So the area of the base of a regular polygon is 1/2 times the apothem times the perimeter. And then we need the formula for the perimeter. So the perimeter of a polygon is the number of sides times the side length. So we've got to kind of work backwards and put all the pieces in the right place. So let's start out with the perimeter. The number of sides of a hexagon, that would be 6. And then the side length, what's the side length? For each side, we've got 10 inches. So the perimeter is 60 inches. And I'm going to go ahead and insert that into this formula right here. So the area of the base, which I'm going to need in my volume formula, is 1/2 times the perimeter, which is 60, times the apothem. Now the apothem is a little different. It's not drawn in here. It's not given to us. Remember that the apothem is the distance from the center of the polygon to the face, or sorry, to the side of a polygon at a right angle. So it doesn't really show us here, but I'm going to go ahead and draw it in. So we've got the center of the polygon. We've got some radii coming off of that center, and then we have at a right angle the apothem. So there's our apothem, and we should be used to, by now, hexagons, because whenever you have an apothem that you're looking for, and it's from a hexagon, well, the central angle measure is 60 degrees, which means that this little angle measure is 30 degrees. So this is 30 degrees. What about this piece right here? This whole distance, the side length is 10. But if I just want half of that distance, then this bottom piece is 5. And I'm looking for the apothem. Well, in a 30, 60, 90 triangle, this is short side, and then this is short side square roots of 3. So the apothem should be 5 square roots of 3. It's a very quick process for the area of a hexagon. So hopefully you're getting better at that. So the apothem is 5 square roots of 3. So half of 60 is 30. 30 times 5 is 150. So I have 150 square roots of 3 for the area of the base. So now that formula gets substituted here. So the volume equals 1/3 times the area of the base, so 150. 150 square roots of 3 times the height. Now the height of this pyramid, did they give us the height? No, they didn't. They gave us 10 inches, which is the side length of the hexagon, and then they gave us 16 inches, which is the what? It's from the vertex to the side of the base at a right angle. That's the slant height. That's not what we want. So what I'm going to do is I'm going to go ahead and draw in that slant height again, but I'm going to draw it along to the side so that you can kind of see what it is that it makes, because I'm looking for the height of the pyramid, not the slant height. So I'm going to draw another slant height over here. And then it's going to go back to the center, and then this bit right here, that's the H. That's the height that I'm looking for. Okay, what was the apothem? The apothem was 5 square roots of 3. And remember that this is a right angle, because the height always creates a right angle with the base of the polygon, or the base of the pyramid, which is a polygon. And then the slant height right here, that was 16 inches. So I have this kind of floating triangle right here, floating right triangle. It's kind of taken a slice out of my pyramid, and I need to figure out the height. And so I have the hypotenuse, which is 16 inches. I have this other leg, which is the apothem, that's 5 square roots of 3, and I'm looking for that missing piece. And so that missing piece can be found with the Pythagorean theorem. So we have h squared, a leg, plus 5 square roots of 3 squared, another leg, equals 16 squared, the hypotenuse. So we have h squared plus 5 squared is 25, the square root of 3 squared is 3, and 25 times 3 is 75. And 16 squared is 256. And when you subtract 75 from both sides, you end up with 181. So h squared is equal to 181. And when you square root both sides, you end up with an h value of the square root of 181, which I'll tell you right now is a prime number. So that's going to go into our formula right here. We weren't given the height, we had to calculate it based on the pieces that we had. So our volume is a little funky looking. What can you take 1/3 of? 150, 3, or the 181? You can only take 1/3 of the 150 because these two numbers are outside of the radical. So 1/3 of 150 is 50. And then what do you do with the square root of 3 and the square root of 181? Those get to go together because they're under the radical. You get to multiply those numbers together and you get to put them under the radical in the answer. So this is 543. Now volume is different than area in many ways, but one of them is the unit. So if we're doing all of our measurements in inches, an area amount would be inches squared, but a volume amount would be inches cubed. Inches cubed. We have the height, which is in inches. We have the area of the base, which is in inches squared, and inches times inches squared is inches cubed. So that's a good example of finding the volume of a pyramid, especially when the base of the pyramid is something that's a little more complicated than just a square. So let's move on to example 2. We want to find the volume of the composite figure. The prisms are right prisms, so there should be right angles here. Okay, right angle here. It's all right angles. So I need the volume of the composite figure. Now volume is a little bit easier than surface area when you talk about composite figures because you shouldn't be talking about like adding surfaces. You have a volume of a figure and another volume of a figure and another volume of the figure, and you add them all together and you end up with your volume of the full composite figure. So we need volume of the first figure plus volume of the second figure plus volume of the third figure, and that's going to give us our total volume. So let's talk about the first figure. The first figure is a triangular prism. So when you find the volume of a triangular prism, that formula is the area of the base times the height. So if I'm looking at just this prism, the area of the base, which is this triangle right here, the area of the base is a triangle. So 1/2 base times height, and then times the height of the prism. So I know this is bad form here, but this is the height of the base, and this is the height of the prism. So we have 1/2. What's the base of this base? The base of the triangle. We've got 4 inches. And then the height at a right angle, what is this height? We'd say it's also 4 inches because they're marked congruent. So that'll give us the area of the base, and then I need to multiply by the height of the prism, and so the height of the prism, remember, is not the height here. It's not from the bottom to the top. It's the distance between the bases. So if you have a base here that's a triangle and a base here that's a triangle, that distance between them would be 3 inches. So 1/2 of 4 is 2, times 4 is 8, times 3 is 24. So that's the volume of the first prism. Second prism, and I'll do this in a second color. So we have a prism here. My formula for a prism is the area of the base times the height. Remember that for a rectangular prism, the base is a rectangle, so we have length times width and then times the height of the prism. So let's say that we've got base down here, base up here, because this figure is filled with rectangles, so we need to pick our bases. So for the base, our measurements are more up here. So the length is 5, the width is 3, and remember the height is the distance between the bases. So the distance between here and here is the same as over here, it's 4. So the volume of the second figure is 5 times 3, which is 15, times 4, which is 60. 60 inches cubed. So now we need to move on, and we need to find the volume of that third figure. Now that third figure, I'm going to switch back to red so that it doesn't blend in with my purple work. That volume of the third figure is the volume of a pyramid, and the pyramid formula for volume is 1/3 area of the base times the height. So 1/3 the area of the base. Well, remember that the base of this figure is a rectangle. And so I want to have length times width and then times the height of the prism. So 1/3 times the length. So the length of this would be right here. So 4. The width. So this distance right here, that would be 3. And then the height of the prism from the base all the way to the vertex, that's 4 inches. So the volume of that pyramid, you can't really take 1/3 of 4 and get a nice number, but 1/3 of 3 is 1. And then 1 times 4 is 4, times another 4 is 16. So total, whenever you want to put together all 3 volumes, volume 1 is 24, volume of the second figure is 60, volume of the third figure is 16. So the total volume is equal to 24 plus 60, which is 84, plus 16, which is 100. And all of our measurements are in inches, and volume is measured in inches cubed. Oops. There we go. Sorry about that. Okay, so let's move on to the next page. The next page, this problem is a little strange, and so instead of solving it, I'm going to give you an answer and we're going to kind of talk about it, because it's not really worth it to solve the problem, but it is worth it to have a conversation about this problem. So it says in example 3, the Rainforest Pyramid in Galveston, Texas, which is at Moody Gardens, is a square pyramid, so its base is a square, with a base area of about 1 acre and a height of 10 stories. Estimate the volume in cubic yards and in cubic feet. Hint, 1 acre equals 4,840 yards squared, and 1 story is about 10 feet. Well, if I need this to be estimated in yards and cubic feet, cubic yards and cubic feet, then that means that I'm going to have to convert one of these for one of the problems, and then I'm going to have to convert everything for the second problem. So let's go ahead and keep things in yards, but I need to convert this to yards. So, how many feet are in a yard? There's 1 yard, and every 1 yard has 3 feet. So I need to convert 10 feet to yards. I don't know how many yards. So I'm going to cross multiply. I have 3x equals 10. If I divide both sides by 3, I get x equals 10/3. So this 1 story is actually 10/3 yards. So I'm going to use this and this to get my answer. Now my answer for the final volume is 48400 over 9 yards cubed. So this is my answer. And I told you I'm not going to expect you to do the problem right now, but I am going to expect you to listen to the conversation that we would be having in class. So it's different whenever you're doing conversions for linear feet versus area versus volume. So if I say that a figure, a square perhaps, so let's talk about a square. If I say that I have a square, and I know it doesn't really look like one, but there we go. If I say that I have a square, and the measurements are, the sides are 1, so all the sides are 1, then that means that the area is 1 unit squared, correct? Because 1 times 1 is 1. Now let's say that I multiplied all of these sides by a scale factor of 2. So if I multiply 1 by 2, I get 2. So all of these sides are now 2. Does that mean that the new area is 2 units squared? Because we went from 1 to 1 and then 2 to 2. Is that correct? No, that's not correct. Because when you try to find the area, you multiply a length times a width, and 2 times 2 is 4. So it's 4 units squared. So what happens is that you're not multiplying the area by whatever this changed by. You're multiplying the area by whatever it changed by 2 times, because you get to multiply it by 2 here and by 2 here. So it's like, instead of length times width, it's 2 times the width. And 2 times 2 is 4. So it's like you're multiplying by multiple 2's. However many dimensions you have, you multiply by multiple 2's. So let's talk about if I have 1 foot, no, not 1 foot, 1 yard, and 1 yard is 3 feet, right? So 1 yard is equal to 3 feet. We found out that we can convert this, and 10 feet is 10/3 yards, but that's not the point, because now what I want to do is I want to figure out what 1 square yard is. Well, 1 square yard, remember, you're trying to find that new area with your new unit. So like 1 squared is 1 yard squared, but 1 yard squared is not equal to 3 feet squared. It's taking 3 and 3 and multiplying it together and getting 9 feet squared. There. And then what about 1 yard cubed? Because in volume we deal with units cubed. And so here, if I'm converting cubic yards to cubic feet, which is what I'm supposed to be doing, if I convert cubic yards to cubic feet, I can't just divide by 3. That's not what I can do, because the volume is changing much, much faster than just kind of a linear unit would be changing. So if I have 1 cubic yard, well, that means that I'm taking a length of a change of 3 and a width of a change of 3 and a height of a change of 3. So 3 times 3 times 3 would be a change of 27. So this is 27 feet squared. So I wish I wouldn't have written this stuff here, because I need to have something out here now, that this is like 3 feet to the power of 1, right? So 3 is 3 to the power of 1, 9 is 3 to the power of 2, and 27 is 3 to the power of 3. And notice that these match. Oh, sorry. It should match. There we go. Cubic yards and cubic feet. So these should match, right? Squared with the squared, power of 1 to the power of 1. So if you're converting, then that means that you need to convert by whatever your scale factor is, and then either cube it or square it, whether you're doing volume or area. So whenever I take my volume answer and I try to convert it into cubic feet, that means that I don't want to just take my cubic yard answer and multiply by 3 because there's 3 feet in a yard. That's not what I want to do, because my volume in cubic yards is changing much, much faster than just regular linear yards are changing. So instead of multiplying this answer by 3 feet, I need to match my units. So yards cubed, that doesn't change by 3 feet, that changes by 27 feet cubed. So I'm going to take my 48400 over 9, and I'm going to multiply by 27. So my volume, these are both divisible by 9, by 3 here. And when I multiply 48,400 by 3, I end up with 1,452,000 feet cubed. So here's my feet cubed answer, here's my volume cubed answer. So it's important to take away from this problem not so much what the answer is, but the fact that whenever you are converting volume or area, you're not just multiplying or dividing by the scale factor. You've got to either square the scale factor or cube the scale factor, whether you're using area or volume. So let's move on to the volume of a cone. We've got a few more problems. So to find the volume of a cone, our formula is the same as the volume of a pyramid. So the volume equals 1/3 area of the base times the height. The only thing is with a cone, with a cone, the area of the base is always going to be the formula for the area of a circle. So this really is 1/3 times pi r squared times the height of that cone. So in example 4, when I want to find the volume of a cone, I'm going to use 1/3 pi r squared times h. So 1/3 and pi are coefficients. The r in this problem is the 16 centimeters, so 16 squared. And then the height I'm not given. That's my height. My height is at a right angle to the base, and I have this triangle right here, which is great, and it's a right triangle, but I'm missing a side length, but I have the other two. So how do I find the missing leg when I have another leg and the hypotenuse? Well, I use Pythagorean Theorem. So I have h squared plus 16 squared equals 34 squared. So h squared plus 256 equals 1,156. When I subtract 256, I get h squared equals 900. And if I square root both of those sides, then I get h equals 30. So that seems about right. It's less than the hypotenuse, 34, but it's much taller than the 16 centimeter radius, so that is logical. 1/3 of 30 is 10. Times pi times 256. So my volume is 2,560 pi, and I'm measuring in centimeters cubed because this is volume. Okay, so we have one last problem today. Actually, we have two, but this last one is something that you haven't seen before. So example 6, we've seen, but we just found the surface area. In example 5, we've not seen anything like this before. It says, find the volume between the cylinder and the truncated cone or frustum. So a truncated cone, truncated means cut. So if you're like saying something and you're in the middle of the sentence and then all of a sudden you stop in the middle of the sentence, that means to truncate, to cut off. So a truncated cone like this is called a frustum. So it has a name, it's a strange name, but it's called a frustum. The radius of the cylinder is 3 centimeters. So this cylinder is 3 centimeters. The distance between the edge of the base of the cylinder, so here's the cylinder and here's the edge, right? So the edge of the base of the cylinder and the edge of the base of the frustum is 9 centimeters. So this distance right here, this is 9 centimeters. And the height of the cylinder is 21 centimeters. So this height right here, right angle, 21 centimeters. The height of the original cone is 40 centimeters. So when they say original cone, remember this was a truncated cone. It was cut off. This is a frustum. So what we want to do is we want to kind of show the rest of the cone and what it would have looked like. So it would have come up here like this, and like this, and this is what we would have had. So we've got this extra piece. So this height right here, from here to there, that height was 40 centimeters. So if that height is 40 centimeters and this is 21 centimeters, well then what's the height of the truncated part of the cone? So I subtract 40 minus 21 and I end up with 19 centimeters. So I need to find the volume between the cylinder and the truncated cone. So I don't want this piece up here, and I don't want the interior cylinder volume. I just want to take all of that out. So my plan is to find the volume of the big cone and subtract out the volume of the small cone, because that got cut off the top, and then also subtract out the volume of the cylinder. So that's the plan. So the volume of the big cone. Remember a cone's formula for volume is 1/3 pi r squared h. So we have 1/3 times pi times the radius of the big cone. Well, here's the big cone and the radius is here, and it's not 9. This part is 9. What is this part right here? That part is 3. So this whole radius is 9 plus 3, which is 12. So times 12 squared, and then times the big height. The big height was 40 centimeters. So we've got 1/3. Let's see. 1/3 of 144 is 1920. Or sorry, 1/3 of 144 is 48. And 48 times 40 is 1920. So that's our volume of the big cone. Now I need to subtract out, so let me do this in a different color. I need to subtract out the volume of the small cone. So again, same formula, different measurements. 1/3 pi r squared times h. So 1/3 times pi times the radius of the small cone, which is 3, times the height of the small cone, which was 19. So 1/3 of 9 is 3. And if I multiply 19 times 3, I end up with 57 pi. And finally, we have the volume of the cylinder. So the volume of the cylinder is the area of the base times the height. The area of the base is pi r squared, and then the height of the cylinder. So pi times the radius of the cylinder is 3 centimeters. And then the height of the cylinder right here is 21 centimeters. So 3 squared is 9. 9 times 21 is equal to 189. So 189 pi. So I need to take 1,920 pi. I need to subtract 57 pi. And then I need to subtract 189 pi. So when I do that, 1,920 pi minus 57 pi is 1,863 pi, and I still need to subtract 189 pi. And when I do that, I get 1,674 pi. This is my total volume of the frustum, and it's measured in centimeters, but because it's volume, this is centimeters cubed. So our plan was to take the volume of the large cone, subtract the volume of the smaller cone off the top that was cut because this is a truncated cone, and then remove the volume of the cylinder from the inside. We didn't have to do anything with surface area. There was no adding in extra surfaces because we're just taking out the space that's in the figure. So finally we have example 6, and I'm not going to work it out all the way because I think as long as you have a plan, then you're going to be all right. You need to find the volume of the composite figure. So it was what looks like a box or a rectangular prism, and then you need to take out the space that's filled up with that pyramid. And so our plan for the volume of this composite figure should be the volume of the prism. And then you should subtract out of it the volume of the pyramid. So let's make sure that your formula has all the right pieces. The volume of the prism, that volume formula is the area of the base times the height. Well, the area of the base is the length times the width. So length times width times height. And you need to subtract out of it the volume of the pyramid. That formula is 1/3 times the area of the base times the height of the pyramid. And the area of the base would be the length times the width because the base of the pyramid and the base of the prism are exactly the same. So times length times width times height. And also notice that the height of the prism, which is 15 feet, is the same thing as the height of that pyramid, 15 feet. So the heights they share in common. So I would take all of the values, substitute them into your big formula, and you would find the volume of your composite figure.